Now we're going to look at another example looking at body fat percentage. Suppose you're a public health researcher and you're examining the relationship between body fat percentage and weight in pounds. You gather a random sample of people and you find a correlation in that sample. But the idea is you want to make an inference about the population so you don't erroneously claim that there's a relationship, which could be due to just random sampling variability. Again, no matter what the correlation in the population, through the process of random sampling, it's possible, but perhaps unlikely, that you obtain a particular correlation in your sample given certain correlations in the population. This is the whole idea of statistical inference. Right? We want to make sure that our findings are not due to random sampling variability, given the fact that we're basing our findings on a random sample from a population. So let's look at the sample correlation between body fat percentage and weight in pounds. So we find that the correlation in the sample is fairly strong, and it's a positive linear relationship. You can see it in the scatter plot. Right? As weight in pounds increases, body fat percentage increases, which is what you might expect. And the correlation is roughly 0.596. Let's conduct an inference though. Let's conduct a hypothesis test. So the null is that the population correlation is 0. The alternative is that the true correlation in the population is not equal to 0. We have a t-test statistic that is quite high, a little bit above 7. Then we have a degrees of freedom that is simply the sample size minus 2. Then we have this p-value, which is almost 0. Right? The probability of obtaining the test statistic we obtained under the assumption that the true correlation in the population is 0. It's very unlikely. It's very unlikely to obtain a more extreme test statistic under that assumption, that the correlation is 0 in the population. So we can conclude that we reject the null hypothesis of no correlation in the population at the alpha 0.05 level, because the p-value is significantly lower than that. If the p is low, the null must go. We also have a 95% confidence interval given to us, and we can conclude that we're 95% confident that the true correlation in the population is between 0.453 and 0.709. We are also given in our output the sample correlation, which is, as we mentioned earlier, roughly 0.596. So we can conclude we do think that there is a true correlation in the population. This observed relationship, this observed linear relationship between body fat percentage and weight in pounds, it's unlikely to be a result of pure random sampling variability. So a few things to know when talking about inferences for correlation. We can use the correlation of a sample to make inferences about the population correlation. The most common test by far in the research literature and in applied fields from sociology to psychology to economics, by far the most common test is two-sided, with a null that the population correlation is 0. We're going to focus on interpreting p-values and calculating confidence intervals using statistical software. And again, the important point here, fundamentally, is that the correlation coefficient, it only measures a linear relationship between two numerical variables. It doesn't apply to categorical variables, and it doesn't apply to relationships that are nonlinear. With that, we conclude our discussion of inferences for the correlation coefficient.